So, am I audible clearly to all of you? Yeah, thank you, Arjun. Yeah, so we'll start for today's session. Okay, so welcome everyone. So, uh, today in the session for the course of strength of materials, the topic is like beam under flexure and shear and the composite beams. So, these are the two topics which have been covered so far in this week by the professor, and you have seen, I hope you have seen the lectures also. So there you have, because flexure was mostly covered in the last week, so that was over. We had already discussion on some of the numerical problems in flexure. Okay, so this week mostly the shear was dealt, the shear stress, how shear varies over the depth of the cross section, how uh, normal stress varies over the depth of the cross section. We have already seen last class, but we'll review little bit that today also because it is necessary. And then we will go for composite beams and we will find how we find the maximum stresses in composite beams. Okay, so that was the we'll do in today's session. And first I'll try to recap the things because it could be a little bit involved for you guys also, the calculations and everything. So just wanted to recap about the formulas, equations which we are going to use today in today's session mostly. Okay, so I'll do first a recap and then we will go into the numerical problems. Okay, so let's do a recap. So we had seen last time the famous flexure formula. Okay, flexure formula, which was also known as Euler beam Bernoulli theory, Euler Bernoulli beam theory, which we have seen. So what we find there, how the uh, how the flexure formula is there. So we have mb by iz is equals to minus sigma x upon y is equals to E upon rho. Okay, this we have seen already last time. So I had told you why we use minus, because, so I'll draw the cross section here for the clarity. So generally what we do, we represent the centroid with the at the origin at the centroid of the beam. So this is our z axis and this is our y axis. So our y will be like in the upward direction it will be positive, in the downward direction it will be negative. So because of that we have to use this negative sign here. So when our y is positive, we know that for a positive bending moment, that is sagging, the top fiber or the top portion of the neutral surface is in compression and the bottom surface is in tension. So to represent that, if we go in this direction where y will be positive and we will find the sigma being negative, that means it shows compression. And when we go in the negative part of y, this vanishes, this sign, and we get tension, which is positive. So for that purpose we use this. Although if you are if you are not finding the in terms of tension and compression, you want the maximum values. So you know where the maximum values occur. You know the maximum value occur as far as you go away from the neutral surface. There the maximum value occur for normal stress or bending stress. Okay. Yeah. Yeah. Arjun has a question. Yeah. Yeah. Yes, yes. That's why. That's why. Yes. That's why we are putting minus. So that automatically it takes away. And our convention is to represent compression by negative. That's why we are putting a negative. Because the positive direction of y is in the zone where for positive bending moment it will come negative. Means it will come compression. If you have a positive bending moment, so suppose you have a beam like this, sorry, something like this, and you have some moment like this. Okay, so moment like this. So this is positive bending moment. Okay, and we know that this surface will be in compression and this surface will be in tension. That we know. So for that only, to accommodate this factor only, because our bending moment will be positive, so to give in positive direction of y a negative sigma, this minus is there. Okay, I hope you understood. This point is clear here. Yeah. So now the one more important thing is to remember that this flexure formula, you might have remembered the lectures, was derived for constant bending moment. Constant bending moment. Okay, it means it was said that when the bending moment does not vary, it remains constant. We have derived this formula. This formula has come up. But when we used in the last session also, we used it for those problems also where the bending moment was not constant. So basically what we are saying that even we have derived the formula for constant bending moment, we can use it even for the case where the bending moment is varying. Okay, so that is one most important thing to remember. Okay, and if somebody asks, right, what happens if the bending moment is varying, so I'll give an example like what to do or how to use this formula in case of varying bending moment situation. So suppose this is my hinge and this is the ruler, correct, and a point load is there, which is a P, and you have seen the photo elastic fringes also for this case in the video lecture. I would request you to at least like pause the video or run the video in that period, because you will get a lot many information. Uh, like I will request you guys to go again and check the case of this loading, where the load is applied here and photo elastic fringes are drawn for stress sigma 1 minus sigma 2, the principal stress. You will see some variation like this, something like this, some variation, and that is very important, because that's how you have learned like how at 45-degree shear and means there is a shear, and that shear is causing tension in one side and compression in one side. That is very much interesting, because otherwise it is difficult, because we hardly in literature and textbooks hardly they derive the equations for these curves. Okay, but there by looking at the video or the picture you can see how those curves are coming. Okay, so that is there. Yeah, so I was talking about how what I mean by this. So what I do, I draw the uh, BMD SFD both. Okay, so the convention is this positive. I'll draw the convention for shear. So positive shear, on the positive face upward is positive and on the negative face downward is positive, correct? So this phase being negative phase, okay, because our axis we are considering this direction, so this phase will remain negative because our axes are like this, so this phase is not a positive phase. Okay, so the SFD I'll draw something like this till the center. Okay, then we have a change here, and then okay, this is negative, this is positive, and here the value is P, here the value is P. Okay, so this is our SFD shear force diagram. Similarly, I can draw the BMD also for this case. So BMD also I'll draw here. Okay, so it will be a triangular variation. Maximum value will be here. It will be PL by 2 or PL by 4 actually at this point, WL by 4 or PL by 4. Okay, how I came to know this, you know, okay, because the reactions will be P by 2, P by 2. Here the reaction will be P by 2, here the reaction will be P by 2. This whole length is L, so this distance will be L by 2. So basically I am just finding at this section the bending moment, so P by 2 into L by 2 is PL by 4. Okay, so that is our BMD. Okay, so now you can see, so this is the section of the beam where the actually the point load is applied. There we are having the maximum bending moment, and then it is varying across the surfaces, across the length of the beam. So basically we had discussed that this equation is only, it has been derived when we consider there is a constant variation of moment, but you can apply also even it for the cases where the variation is not constant. Just you have to choose which cross section you are applying these equations, and accordingly you will choose the MB. Okay, so suppose you need to find at cross section this, suppose, okay, this I will call 1 1. So whatever is the bending moment at 1 1 you can find out using this bending moment diagram, and you have to insert that value here in MB, and subsequently you can find the sigma value and IZZ being remain for the cross section. So basically the catch is in using the correct MB, correct value of MB. So wherever you want to find on the cross section on the length of the beam, that moment you have to choose. Okay, if I want to find here, then you have to choose this moment. The same equation will apply. Okay, so one thing is this. Now another thing, from the same flexure formula you can see, if I take these two parts, so you can see how can I represent sigma x. Sigma x by y minus of sigma x by y is equals to E by rho. Okay, so from this same flexure formula I can write sigma x is equals to minus y by rho into E. Okay, okay, and you know what is the strain also. You know what is strain, epsilon x. Epsilon x is nothing but minus y by rho. So basically this you should remember. And what is rho? Rho is the radius of curvature. Okay, radius of curvature, and curvature will be 1 by rho. So curvature, what is curvature? Curvature will be 1 by rho. This is curvature. Okay, so now in this we have to remember this one. This will be important for us, because if we know curvature or radius of curvature, we can find the sigma. Okay, and also we should remember how the epsilon is varying, that is the strain is varying. So our beam bending theory is based on the fact that the strain varies linearly along the cross section. So okay, so strain remains varies linearly along the depth of the cross section. Okay, So this is important. Then comes the movement. Sometime we need to find force also. So force I will tell first. So force over the cross section. So the formula for that is, so what I meant by force over the cross section means, suppose this is a cross section of a beam, and suppose the stress varies like this. Okay, it is compressive here and it is tensile here. Okay, it varies like this, some depth d of the section, some width b. Okay, now if you need to find the total force due to this compressive stress, what is the total force acting over this surface? So basically we have to use this formulation which I am going to write here. So how we write? We find integral sigma x into dA over the area A. Okay, so this way we write our force. Okay, because there are two equilibrium conditions we have. One is called force equilibrium and another is called moment equilibrium. Okay, so force equilibrium is used in this scenario, in this scenario where we need to find the total force. And actually what happens, how we find this neutral axis? I have drawn this surface, this axis which is passing through where the stress as well as strain is 0, this point. Even if I draw the strain profile, strain will be 0 on this surface. So how to find this neutral surface is also using the force equilibrium. Okay, so what we do, we actually equate the forces in the two, in the top portion of the beam and the bottom portion below the neutral axis. We equate it. So if you remember in the second lecture of last week, where the professor is solving reinforced concrete beam problem, so there he has used the same principle to find first of all KD. KD is the depth of the neutral axis from the top fiber or the top surface. So how to find that KD? He has used the fact that the forces due to the concrete in the compression is equal to the force due to the steel reinforcing bar provided. So I would request, that is very interesting problem and a very interesting application of composite beams. You should, if you have seen, very good. If you have not, you should go back and see that. It is in the second lecture. Okay. So this one, and then we have moment. Okay. So how we find moment is minus area or integral area sigma x y dA. Okay, so this is how we find moment. M is equals to minus of integral area sigma x y dA. Okay, so this gives the moment equilibrium. So using moment equilibrium, we basically find then what is the bending moment capacity, or basically it gives us the way to find different other things. So what you can do now, already how sigma is represented in terms of y, rho and E. So you can substitute it here. Okay, you can substitute this here, or you can substitute this sigma x here, and you can do further calculations or further manipulations. Okay, so for that, okay, so what I will, and that in case, yeah, Arjun has a question. Yeah, 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 Yeah. So dA, yeah, you are correct only. Here the dA represents the small area. So how you will do? You are right. The further process is like you will say at a distance y, you will take a very small strip like this. Okay, what I will do, I will show you. See, you will do what at a distance y from, suppose you want to do from neutral axis. So you will do, say at a distance y from the neutral axis, you take a very small strip. Now what is the width of this strip? B. And what is the thickness of this strip? dy. So now what is your dA becomes? dA becomes b into dy. That is the small area, and that you insert here, and then your limit of integration, this whole formula changes to f is equals to integration sigma x y dy, and now your y varies from what? Minus h by like I will do in the other term. So minus d by 2 to d by 2, correct? Yeah, no, I am considering from neutral surface, but see, this whole depth is d by d, no. So half of it will be above and half of it will be below, no. So my integration limit should be from minus of d by 2 to plus of d by 2. Y will be minus d by 2 at this surface and plus d by 2 at this surface. Yeah, that is something different, I think, in a different scenario. Okay, I think that you are talking about where we do the shear problem. Maybe it is in shear. Okay, right now we are just doing the forces that he has done for finding the first moment of area or first moment of inertia, that q. So to do that, we'll come to that also. Okay, yeah. So this way we do actually. So what we do, instead of, because we don't like how to convert this dA into simpler things, that is how it has been done in literature. Okay, you take a very small strip and you know the width remains b. So okay, I am missing, I think, something here. I should write a b instead of y. Sorry, yeah, it should be b, not y, dy, because I have replaced dA with b into dy. Correct. So sigma is constant. If it is a constant, then it will come outside the integration. B is a constant width, so it will also come out of the integration, and integral dy will be only there. But you can understand that in this case, because the if suppose the beam is in equilibrium, the total force acting above the neutral axis and the total force acting below the neutral axis should be same. So the sum of these two forces will be 0, but that's the fact is used to or exploited to find the neutral axis. So what we do, we find some of these forces above neutral axis, then we find the forces below neutral axis, and then we say the sum of the two should be 0, and then it gives us the value of the neutral axis depth. Okay, this depth we get. So it has been used in that question which professor solved in the composite beam case. It's a rectangular beam made of reinforced concrete, I think M30 reinforced concrete, and it's a typical civil engineering question, very typical question. So how you find the neutral axis, and then how you find the movement or how you design the beam, kind of. Okay, so that is there. Then we saw in the lecture the shear stress variation. Okay, shear stress variation over the depth of a beam with rectangular cross section. Okay, so we saw this in this these lectures only. So what is there? Let's suppose there is a beam, something like this. So we had already seen how the strain varies. This we have seen. The strain remains linear, something like this. Okay, So this is compressive strain, this is tensile strain. Okay. Epsilon. Then we have seen it's epsilon x. The stress variation. So stress will be something like this. This is again compressive, and this is tensile. Sigma. So now comes the variation of the shear over the depth. So we have seen that shear varies something like this, and it becomes maximum at the center or at the neutral surface, and 0 or minimum you can say, or 0 at the top and bottom surface. Okay. And then what professor showed in the last week's lecture was very interesting, that he showed, and I had told you that he will show it next time. Last time only I told you why we are ignoring the effects of shear when we are using the flexure formula. Even you can see, even though we have shear force coming up, but after that also we are using the same formula. Why is it so? Why are we not worrying that, oh, there is a shear, we can't use the same flexure formula which is only valid for a constant variation of bending moment? Okay, the bending moment should be constant. For that only the flexure formula is derived, but still we are using for a variable variation of the bending moment also, because you saw that the magnitude of the shear stresses which comes are like 1/10 of what the magnitude of the bending stresses are. He showed you that by plotting it in a scale with the bending stresses. So the shear stresses are somewhere 1/10 to 1/20th of what the bending stresses are, and that is why we tend to ignore them. And why it is coming? It is coming because in the cross section which we have chosen, it is not like coming universally. It is actually a cross section and geometry dependent. Okay, you go back, if you go back to there, and if we will get time today, we may look in that also, because it is a geometric dependency, then only it is coming like that. Don't think that it will come every time, because we have chosen our geometry of the beam, length of the beam or the depth of the beam, which we know we call generally as shallow beams. We are having or slender beams, basically we are having very larger length, or the depth of the beam is very small compared to the length of the beam, and that is why the shear is coming up like this. Okay. So if we don't follow that, the situation would be different. So that is why generally we, even though the shear will be there, we design for the shear, but while calculating the deflection, which you may see in the next session, you will find that the deflection due to shear we very rarely we take. In the case of slender beams, we never calculate actually the deflection due to shear, because as you saw how the contribution is of shear stress, so the contribution in the deflection is also very less. It is like some within 5%. So we tend to ignore it. Okay. So what formula we derived in this was, we found that tau xy is equals to V into Q upon Izz into B. Okay. This we saw, the derivation of this was done in the lecture. So V was the shear force, okay, on that cross section, or on a particular cross section, okay, because the shear force will also vary along the length. So it is, this equation is also like wherever you want to find, you can find. You can see the shear is varying. Okay, shear is varying. So here actually it is a constant, but if suppose I give us another loading or some other loading where shear varies, so you can have different values of shear at different cross sections. So you can choose, but what interests us most is that we tend to find at the maximum places. So here at the support the shear remains maximum, and in this case it remains same throughout the length also. So our interest always remains to find wherever it is maximum. Okay, so we generally use the maximum where V max is coming. Okay, then Q is first moment of inertia about the neutral axis for the region between the top surface and y. That means, so suppose in this cross section you have asked to find the shear force at this the shear stress at this level, which is at y. Okay, from the neutral surface you have been asked to find the tau xy value at this y. So what Q represent is, it represents the first moment of area of this area about the neutral axis. Basically it asks us to find the first moment of area of this area which I have shaded about the neutral axis. So one way in simpler geometry, where the geometry is simple, rectangle, triangle, okay, so in those problems where the geometry is simple, what we can do that we can find the area, this area, and then we can find the centroid also of this area. Okay, we can find this area and the centroid of this area, and then area of this shaded region multiplied with this distance between the centroid and the neutral surface will give us the Q. So basically Q becomes A into y bar. You might have remember this also. Q becomes A into y bar. So A is not the cross section area, is it basically A is this area which is shaded. So as this y keeps on changing, this area, if this y keeps on coming down, the area keeps on increasing. So if y will be this, the area will be more. Okay, so and y bar is the distance of the centroid of that area with the neutral surface. So that's how we can find this first moment of area here. And I ZZ remains the moment of inertia about the ZZ axis, and B you know is the width of the beam. Okay, so this also is one of the important concepts which we may need to solve some of the problems. Okay, so I did this because it's little bit tricky and a little bit involved also. Okay, now what we can do, we can go to our problems for today's session. Okay, so let's look at the first problem. Okay, so first problem here says that a wooden beam AB supporting two concentrated loads P has a rectangular cross section of width B is equals to 100 mm and height H is equals to 150 mm. Okay, so some beam is given which is supporting some two concentrated load, wooden beam. You can see that P load is given, how load is applied. So this is basically generally called 4-point bending, because there are 4 points at which loads are acting. These are the 4 points. Okay, sometimes also called 2 point, but 4 point also it is called. Okay, so now what is the distance from each end of the beam to the nearest load is A equal to 0.5. So the A value is given this distance and this distance of 0.5 meters. Okay, now determine the maximum permissible value P max of the loads if the allowable stress in bending. So it has been given what is the allowable stress in bending is 11 MPa for both in tension and compression. Okay, and the allowable stress in horizontal shear is T allowed is equals to 1.2 MPa. Disregard the self weight of the beam. So here we don't need to worry about the self weight, we can disregard it. So it is asking what the maximum value we can put that of P load, which will be under these values of allowable values as given. Okay, so we basically need to analyze this to find what is the maximum value of P. And obviously we have to check this beam for two conditions. One is for the bending, another is for the shear. Okay. So let's start with this problem. So I will copy this figure. Okay. So first we will do what? First we need to find what is the maximum shear and maximum bending moment is going to come. Okay. First of all we should know that. Okay. So what I will do, I'll just draw a sketch for the representative sketch for the bending moment and shear force. I am not going to go into details of that, okay, because you are already aware of that. So I will just draw that to make sure you understand what is the thing. So I will directly draw here below this figure. Okay. So first I will draw the shear force. Yeah, like this. So you can see here. So in this case you see that the reactions will be also same, P and P. Okay. So variation of the shear force will be something like this. First it will be negative, then till the first load it will be like this, then it will be 0, and then it will increase to this, and this will become again here like this. So something like this, it will be negative here and positive here. Okay. And in the region where this load is P, between these two loads there will be no shear. Okay. You should know why it is no shear. The next I will draw the BMD, and you will, I hope you will understand from there why there is no shear in this region. Okay. So the BMD will be something like this, like this, like this. Okay, so this will be P, this will be P, this will be P into A, this will be P into A. Okay. Now I hope you saw why it is 0 here, because the bending moment between these two loads is constant. Okay, and you know one more formula, I will write it there here also. One more formula you know, or I will do it here. But you know that how you find V shear force is, it is dmz by dx. Okay, it's V is nothing but derivative of the or slope of the bending moment. So if your bending moment is constant, so what is the derivative of constant? 0. Okay. So that's why the shear force is 0 between these two loads. Between these two loads, shear force is 0. Why? Because the bending moment is constant. Okay. So basically between these two loads, the beam is subjected to pure bending moment. But in this region and in this region, both bending moment and shear force exist. Okay. And that is why this test is very famous, because it creates the bending moment, pure bending moment in this region. That is why this test is so famous. Okay. Okay. So we have drawn the bending moment as well as shear force diagrams. Okay. Now what I told was the objective, because here we need to be worried about we want to find the what is the maximum permissible value of the load which we can apply. So obviously our interested in maximum quantities. Okay. So what I will say what is maximum shear. So what is the maximum shear? I will just disregard the nature of the shear, whether it is positive or negative. So I will say it is P. P is the maximum shear. Okay, and similarly, what is the bending moment maximum? So we'll find that this is nothing but P into A. Okay, and we know A, so that's not an issue, but what we need to find, the P. Okay, now the question says that if the allowable stress in bending sigma allowable is 11 MPa, because it is made of wood, so obviously the strengths will be very less compared to the steel. Okay, so sigma allowable is 11 MPa, and tau allowable is just 1/10 of it, 1.2 MPa. Okay, so I'll rewrite those values here. So we have sigma allowable is 11 MPa and tau allowable is 1.2 MPa. Okay, so let's focus first on bending stress. Okay, bending stress. So what we have our famous equation mb upon Iz is equals to minus sigma x upon y is equals to E upon rho. Okay, okay. Now, do we know what is the maximum bending moment? We know. So we know something. Do we know the cross section properties? We know. We know this. Do we know what is the maximum allowable stress? We know. Do we know where it will occur? That also we know. In the cross section where the maximum allowable will occur. So we don't need to consider this. Okay, here we will be just happy with these two terms. Okay, and because we are working, or we are concerned here about the maximum quantities, so we can even drop off the sign term also. Okay, before that I'll draw the cross section. So I think the cross section is 100 mm in width and 150 mm in depth. Okay, that is the size of the cross section, I think. Yeah, height is 150 mm and this is it's a rectangle cross section. Okay, okay. So you know where the neutral axis lies for a cross section which is a homogeneous cross section, means it is consists of one material. Neutral axis lies at the midpoint, like it lies at the mid surface, so it should pass through the centroid itself. Okay, so somewhere here it will be somewhere like this. So this will be your neutral axis. Okay, okay. Now you know, because it's a positive bending moment, so this will be in compression, this will be in tension, you know, but we are right now interested in the positive or maximum quantities, so I will just talk about that. So what we do, we put our values. So first we have PA, so PA by Iz, I will find Iz is equals to minus sigma allowable, I will drop the minus as I told, no need of minus, sigma allowable on Y max. Okay, okay, where it will occur, the maximum bending moment will occur at the maximum Y. So our bending moment maximum will occur either in this surface or this. Here it will be in compression, here it will be in tension, first of all. So this is our Y max, this length is our Y max. So I will mention it in the figure. This is for us Y max. Okay, okay, that is sorted. Now we need to find Iz. So this neutral axis itself is a z axis. So Iz will be what? Okay, okay, good, good. So it will be b d cube by 12 about that axis. Arjun told 28.12 into 10 power 6 mm power 4. Okay, so this will be the value of Iz. Okay, okay, and then what is our sigma allowable? We also know that sigma allowable is 11 MPa. Okay, then what is Y max for us? It will be half of that, so it will be half of the depth. half of this, yeah, so it will be 75. Okay, 75 MPa. Okay. Sorry. It will be mm, 75 mm. It's a distance. Okay. So what I do, I put all these quantities here, or A also I will put. What is A? A is given as 0.5 meters. So I will convert it into mm, that is 500 mm. Okay. And what I will say, the value of P from this, I am calling it as P bending, because it is obtained from bending by considering the bending. So I am calling it just like P bending to make sure that I don't mix up. Okay. So what I will write here, P bending into A is 500, okay, divided by our IZ is 28.12 into 10 power 6 is equals to 11 divided by 75. So P bending will be 11 into 28.12 into 10 power 6 divided by 75 into 500. So if you guys can help me with this calculation. What will be the value of P bending? P bending will be, okay, means you are getting 8250 Newton, I think. Okay, 8.25 kilonewton. So we obtained the maximum value of the load P, so that the stress in the bending stress at the bottom fiber or the top fiber, because you know the neutral axis will lie at the center or will pass through the centroid of the section, and same value of compression and tension stresses will be there at the top and bottom, just the sign will be different. So it doesn't really matter here, what matters the value. So I inserted that value to obtain the value of P bending of 8.25 kilonewton meter. That means if your P exceeds this value, if the load applied exceeds this value, your stresses on the top and bottom fiber will exceed the allowable value. It will exceed the allowable value. Okay, and you don't want that. Okay, so this we did. Okay, now come back to the shear part. Okay, we have done the bending through bending stresses. Now we'll analyze it with the shear stresses. Okay, now we have to look up for the shear stresses. Okay, so what I do, I'll draw first a cross section. Okay, this is my neutral axis. Okay, and you know what is the variation of the shear force, shear stress on the cross section, shear stress. So you know something parabolic which is 0 at the edges and maximum at the center. Okay, that knowledge we have with us. Okay, it occurs maximum at there. Okay, so what we do, we directly go to our expression which we just saw. So we saw that tau xy is what, V q upon I z z into B. Okay, now we'll find each one of this one by one. Okay, so first is our V, that is a shear force. Okay, so first of all we have to look where the maximum shear force will occur. So we have seen from the, and that knowledge we can get only by shear force diagram. So you can now see why what you did in the earlier course of engineering mechanics is important to understand the strength of material or mechanics of deformable bodies. Because if you don't know where the maximum shear or where the shear will be higher or where the shear force will be more, you can't decide on which section you have to work. Okay, so when we know this, we have this knowledge, then only we can do it. So we have the knowledge between this points the shear will be high, okay, and this sections will be having subjected to maximum shear of P. So P is the maximum shear which we are getting. If we don't know that, you can't proceed further in this problem, okay. And to make, if something has to be changed, the only thing you can change is the condition of the beam. You can change it to some other beam, or you can change it to the loading condition could be changed. Instead of 2-point bending, it could be a UDL, uniformly applied load, or uniformly distributed load, or something triangularly varied load, something like that, okay. So shear force, so what will be the maximum value of shear force? We found that it is P, okay, and it is acting near the support at C, between the support and the load, it is P, remains constant, okay. So I will call it as P shear, okay, again to demarcate from the other one we found from bending, okay. Then comes the IZZ. So IZZ remains the same, which is 28.12 into 10 to the power 6 mm power 4, okay. And then B is the width of our beam. So this is the width, we know that already. Now question comes the Q, which I told is, if we simplify, will be A into y bar, okay. Otherwise it is nothing but the first moment of area. It will be basically integral y dA over the area, okay. In terms of integration, it will be written like this, integral y dA, okay. So, but this is a rectangular cross section, it is easier to do it here. So, what I will do, I will use the Q into AY bars formulation only, okay, because it is easier here in this case. So, okay, now we know what is the, where is the neutral axis. So, neutral axis will be just exactly at the mid depth, okay. So, it will be, sorry, this will be 75 mm from top, and also this will be 75 mm, okay, from here mm, okay. Now, so I have this knowledge that the shear stress is maximum at the center or at the neutral surface. So I will write here shear stress due to flexure is maximum at the neutral surface or neutral axis, okay. That knowledge we have with us. So the knowledge is required to find this Q is A into Y, because that's how my A will be decided, which area I am talking about. So because I will be finding the shear stress at what, at this surface. So my objective is to find shear stress at this surface, because there only I will find the maximum, okay. So I am considering this full area, this area, okay. Now if I ask where the centroid of this area lies, so again you know where the centroid of this area will lie. It will lie somewhere here, which will be how much distance? Half of this 75, that is 37.5 mm. It will be just half of this, okay, correct. So now also I know the area, so let's find it out. So Q will be, what is that half of area? So this area will be what? This area will be what? 75 into width. Width is how much? 100. Okay, I'll mention that 100. This is 100 mm width. Okay, so Q is 75 into 100. Okay, and into y bar. So y bar I just found from the neutral surface. What is the distance of the shaded? What is the distance of the centroid of the shaded area? That is 37.5. So this will give me some value. If you can calculate this, what will be this? 20.125 into 28.125 into 10 power 4 mm cube. Okay, so this I found Q, and IGG I already know, width I already know. Now I know everything. So basically my tau will become tau allowable. Okay, that will become tau allowable, and it will be 1.2 MPa. So what I will do, I will put everything here. So 1.2 is equals to V, I don't know, so P shear, Q is just this 28.125 into 10 to the power 4 upon IZZ. IZZ is 28.12 into 10 power 6, and this into B is 100. Okay, so let's see what values comes from here. P shear, I think we can cancel these two, and this we can also cancel, so it will be also 100. Okay, and then this will become 120, and I think it will come around 12 kilonewton. So it will come 12 kilonewton. Okay, so from P shear, from the shear case or shear stress, we found that the maximum load which we can allow only if we consider shear is 12 kilonewton. Okay, and we found from the bending we are allowed to have 8 kilonewton or 8.25 kilonewton. So basically what will the maximum value? The minimum of the two. Okay, we can't, because if we allow more than 8.25 kilonewton load, it will not have any issue with the shear, but it will already be above the allowed limits in the stresses will be above the allowed limits in the bending. So that's why minimum of the two. So we will have maximum permissible load is minimum of the two, P bending and P shear. Okay, so P max will be 8.25 kilometer. Okay, so this is how basically we do this, and we find how the allowable or the maximum load is, and even the same procedure is mostly followed if we design. Okay, so in a similar manner, if we design also, we follow the same procedure, just that we, in that case, we don't know the value of or we don't know the exact value of height and the or depth and the width. We have to fix that. So basically what we do, we assume
please switch off the lights. I just wanted to check whether someone is here or not.
Yes.
Please switch off.
So we just reduce, we just see the depth and the width, and accordingly we find the values. Okay, in the case of design problems, wherever when we don't have design problems, we have analysis problem, in that these values will be given and we can find the various quantities. Okay, now so this gives us an idea how to incorporate for the shear also, and the same procedure as I told will be used in even design problems. Okay, so you have a shear check, you have a bending check, okay, in design. Okay, now let's move to another problem for today. So this is also one of the interesting problem. In this what we have that sandwich beam, so it's a big problem for composite beams. So composite beams means where the cross section or the beam is made up of more than one material. Okay, so the meaning of composite beams is composite beams mean beams made up of more than one material. That is the meaning of composite beam. Okay. So here what we can see, you have a different material here and you have a different material here. Okay, and the same thing has been repeated below. So let's go into the question, but it says that so a sandwich beam having aluminum alloy faces. So basically these are the faces of the beam, this one and this one. These are the faces of the beam, enclosing a plastic core, and this one represented in a grayish color. This one is the plastic core. Okay, and these blue colors are the faces which are aluminum alloy. Okay, so there are various reasons why we use uh, why we use the sandwich beams or basically composite beams. So most of the time it is for the purpose of strengthening. Okay, so we may expect some, or like sometimes what happens that maybe our suppose our in this case our plastic beam, which is the core, is very good in shear. It can resist the shear, but it is not able to take higher amount of tension, basically the bending. It is not able to take more bending. So what we do, we reinforce it with by putting some plates or some sections of some other materials which are of high strengths. Okay, so you can see here that this material is being put away in a way which is parallel to z axis. Okay, so always remember, if anything has been added to a beam parallel to the axis of its bending, because this is the axis of bending. Okay, so if anything is being added parallel to it, that means its main contribution is in the bending, so it will resist the bending. So that is why this has been introduced here. Okay, so there is a sandwich beam having aluminum alloy faces. So these are aluminum alloy faces enclosing a plastic core. This is a plastic core, is subjected to a bending moment of 3 kilonewton meter. So it has been given that bending moment in this case is 3 kilonewton meter. The thickness of the faces is 5 mm. So this face is 5 mm, this face is 5 mm, and then modulus of elasticity is also given. So E1 is faces is E1 is 72 GPa. Okay, that is the value for aluminum. The height of the plastic core is HC. So HC is given 150 mm, and its modulus of elasticity is 80 MPa. So you can see that how less. That other one is 72 GPa, and this plastic core is 800 MPa. Now the overall dimension of the beam is this 160 into 200. Determine the maximum tensile and compressive stresses in the faces and the core. So we need to find what is the maximum value of the stresses are in the faces, and what is the maximum compressive tension, and what is the maximum values in the core. Okay, so let's start with the solution. So what I'll do, I'll copy the figure. Okay, so let's look at the solution. So first of all, what I have told you that in these problems, what is there that you need to find the where is the neutral axis. Okay, that is the first challenge, because you know that the cross section now do not remain as it does not remain cross section of same material. There are two different materials are here. Okay, so in this you can see this is a different material, this is a different material. So we have to first of all ascertain where the neutral axis will be, and I had told you in the starting of the session itself that we have with us two different things which we can use in this first is the force equilibrium, and another is the moment equilibrium or moment equation, I can say, or equilibrium, whatever you say, equilibrium or moment equation. So we have these two only. So in this case, now let's draw the cross section. Okay, so this is the extra thing here, and this is the extra, and this is the neutral surface. Okay, so first I'll draw the variation of the strain. Okay, so you remember that how the strain varies. Strain will always remember that strain always varies linearly. Okay, and you have seen in the lecture also how professor has shown the strain varies. Even in the sandwich beam, there won't be any disturbance in this at the surface where the two materials are joined. Okay, it will be continuous. Okay, because to ensure the compatibility. Okay, so there should be the compatibility between the two. Okay, on the surface of this plastic and the aluminum, the two are attached very perfectly. So strain varies linearly. Okay, so this is our strain profile epsilon. Now the interesting part comes with the stress. Okay, now you know that yeah. So if I draw the profile for stress, so by inspection we know what is the E1 of means what is the Young's modulus of aluminum and what is the Young's modulus of plastic. So by intuitively we can say that because the Young's modulus of plastic is lower than the Young's modulus of the aluminum, obviously the plastic is going to take lesser amount of load compared to the aluminum. So obviously it will generate less stresses compared to aluminum. Hence the variation will be something like this, and then there will be a sudden increase in the stress, okay, at this interface, and then it will also vary linearly like this, and similar thing will happen at this end. Okay, similar thing will happen at this end, and sorry, and it will also vary like this, correct. So this will be the variation of stress, and this will be compressive here like this, compressive, and will be tensile here like this. This is for stress. Okay, so now as I told, this neutral axis we have to fix, and which is very important. Now I told that we generally use the force equilibrium to find the neutral axis, where the neutral axis lies. Okay, so what we will do, we will do the same, just I will show you, because this is a case of a section which is still remains symmetric, bisymmetric. So you can see there is a symmetry along this, and there is a symmetry along this y axis and z axis. So although I already know, and you also already know, that the neutral axis will be at the mid surface only, but still I will just give you a formulation how you do that, how you come up with that, or how you which formula you use. Okay, so as I told, this I will call above the neutral axis as 1, and everything below the neutral axis I will call as 2. Okay. So what I invoke is, I say the total force due to the portion above the neutral axis is integral A1, and the total area I am saying is A1. Okay. So, A1 comprises both this whole A1 and this whole A2, areas of both the plastic core as well as aluminum above the neutral axis is A1 and the plastic core and aluminum below the neutral axis is A2. I write sigma x into dA as I told you how to find force, this, and plus I will add, or I will say sigma x1 also, this to show, and A2 sigma x 2 dA is equals to 0. Okay. Now, what I can do, I can then further divide this sigma, because this full is not of one material, this is again of two materials. So, I can do what, I can divide it again this part into two parts, one will be of aluminum and another will be of plastic, that I can do. Similarly, exactly same this will be done in two parts. Yeah, Arjun. Yeah. 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 So, that is what. So, yeah. So, you remember how this will come, how sigma will vary. Uh, uh, yeah, here. So, you see, I have already incorporated that here. So, as soon as I put there this, so you know, if I will put for A1, so y will remain positive, y will not change, y will be positive, correct, and it will vary from 0 to h by 2, and for the A2 this y will become minus y, and it will vary from h by minus h by 2 to 0. So, this will automatically will take that care. I was about to put this there, do not worry, I will put it there itself. Yeah. Okay. Yeah. Okay. So, when you substitute this in terms of the values of sigma, which we have just seen, what it finally forms? It forms something like this. It becomes E1 y1 dA plus integral E2 y2 dA. Although, because as I told, you can write, I am writing it in a very general sense, because I am not going into that detail, we have to solve further. But what I have said, this we can divide into two parts, one part will be only for the aluminum, one part will be only for the plastic core. Similar we can write for this part here, aluminum and plastic core. But what I am trying to tell you, at the end you will get something like this, which should be 0. And if you say your E1 and E2 are constants, these two quantities are constant. So, what happens? You can take E1 and E2 outside, E1 as outside y1 dA and E2 outside y2 dA is equals to 0. Okay. So, what is this? What we call this quantity? This is nothing but first moment of area only, first moment of area, correct. This quantity is first moment of area, these both quantities are. So, basically using this equation only we find the value of the neutral axis. Luckily in our case, what we are using, in our case it is a doubly symmetric section, means the plates of aluminums are put up as well as below. So, obviously the neutral axis will not change, it will remain same. Okay. So, it will be at the mid depth. So, that I just wanted to make you aware that how if some problem comes where the plate is only in one portion, this portion only plate is there, there is no plate here, then you have to invoke this force equilibrium to find the neutral axis. Okay. And that has been done in that I told in the composite beam lecture, I think lecture 2, professor has done with the reinforced concrete beam with the reinforced concrete beam with the reinforcing bar and M30 concrete, and it is a very beautiful example of this kind where you have only the way only the strengthening given in the below part, because you know that only reinforcements are given in the tension region. Okay. Okay. Yeah. Yeah. Okay. 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 So, I will write here. So, see your integral a1 sigma x1 dA you can write as integral a1 aluminum sigma x aluminum dA plus integral a1 of plastic sigma x plastic dA, like that you can write, in which you will only consider. So, this part first I will discuss this part. This part is just this part, okay. Only this part where plastic is there, that is this part, basically you are finding that area, okay. And the aluminum part is only this part, this very small thickness T thickness part, okay. And similarly we can write for the below part. Understandable? Is fine. Okay. So, that is how we just like two areas. So, we are dividing between this one. So, basically we have to do integration for full. So, what we are saying, we will integrate first this and then we will do the integration for this. Okay. Okay. Yeah. So, we will assume. So, that is what. So, you will say that suppose this distance is suppose some k times of full depth, okay, come k d. You will assume that this depth is some full time k d. Okay. Now, you can find for this much using that k d value. You can find the plastic one, no? This one you can find area using that k d. Then you know how much is this remaining, this is nothing but d by 2 minus k d, only this much is aluminum. So, this distance is what, d by 2 minus k d. So, you can find this aluminum also. Yes. So, you have to actually put the limit of integration. So, you will put from, if you are going from this direction, so you will put k d to d by 2 for aluminum case, or for the plastic case you will put from 0 to k d, correct? Correct, no? For this is plastic, no? I will mention this is plastic, this is plastic, this is aluminum, and this is aluminum. Okay, where is y0? This is y0. That is correct. This is y0, that we agree that this is y0. So, everything will be measured from here, everything will be measured from reference. I just said that this total depth of this y0 or this neutral axis is some k d, okay, this full depth. So, first you will do, or you can even say from the below depth, you do not worry, because you already know this thickness. You just take from the plastic only. You say plastic depth this much is k d, okay, and you know the full depth being d by 2. Okay. Yeah, so either you take d by 2, if you don't take d by 2, that's also fine, you just take t. So you know this kd, you take t, so the full depth will be, I am writing in another sense, now I am doing a reverse way. So this will be, I will write with the proper way, this will, suppose this is kd, this full will be kd plus t. K is just a factor, okay, don't worry, it's just a factor. When k is some value between 0 and 1, so it's just a factor. So this full depth will be kd plus t. So what we can do now, using kd we can find this plastic thing, the force. I don't know k, d I know, I don't know k. Okay. And using this kd plus t, I can find this variation of the for the aluminum, because here, see, here it is 0 and varying to some value. So it is a triangular variation, but you just remember, here it is not a triangular variation, here it is a trapezoidal variation. Okay, it is not a triangle, no, there is already a value of yeah, it is a linear with trapezium, means non-zero. So your values will also vary, what I am trying to say. Basically this equation tries to find this area and then multiply with the width, that is all this does. Okay. Yeah, b into dy actually, yeah, the last, yeah, b into dy, and your for plastic, suppose first I will write for plastic. So for plastic, your limits of integration will vary from 0 to kd, for only for this part I am talking. Okay, it will, this is 0, okay, correct, this plane is 0 and it will vary till kd for plastic part. For aluminum it will vary from kd to kd plus t, correct. T is already known, it is given, thickness is given, aluminum thickness is given, only unknown is K, quantity K. D is also known, okay, only quantity K is unknown, which it will come actually as a quadratic equation. So you will have two solutions of it, one will be negative most probably and one will be positive, or one will be any solution which is between 0 and 1 and positive is the answer. Yeah, so that kd you can, and in this case you will find it is just half, it will be 0.5, because it's a bisymmetric beam, because the symmetry, by adding the plates, symmetry is achieved. So that means we know that neutral axis passes through the mid height. Okay, neutral axis passes through the mid height. Okay, that means it will pass through, the total depth is given, I think 160. Okay, so what I will do, you can see the total depth is given is 160, this thing is 160. So this will pass along with z, wherever z is written, that will be only the neutral axis, this axis, and it will be nothing but 80. So this distance will be 80 from top, and from this it will be I think 75. So half of 150, it will be 75. Okay. Okay. Now coming to, so we have already, as I told, we have already used force equilibrium. We found using that the neutral axis, and luckily for this problem we already knew the neutral axis will lie at mid height. Now we have to consider the moment equation. Correct? We have to consider the moment equation. So what we will do? So we have, I just discussed in the initial part of the session that how moment is written. So this was the way moment is written. So m is nothing but minus of integral over the area A sigma x into y dA. Okay. This is how the moment is written. Okay. So I will also, we will also use the same. So these problems actually they are little bit involved, okay, mathematically. So you have to write moment mz, which is what, minus of integral over the area sigma x y into dA. Okay. So what happens? So this we want to find mz. So what I will do? I will find sigma. What is our sigma? It is minus y e by rho. This we know. So I will substitute it there. Correct? This is fine. We have just seen. So if I substitute, it will be area E by rho and y square dA. Correct? Minus minus gets positive. Okay. E by rho. Yeah. Now is your E constant throughout? Is there is only one E throughout the depth? No. There is no one E. There are two different E's. That means you have to break this down into two parts. mz is equals to integral A 1, which is representing the one material 1, y square dA plus integral A2 E2 upon rho y square dA. Correct? Till here no issue. Simple. Because if E would have been constant, that's all, end of the problem. I will take this E and P rho outside. I will say integral y square dA is called IZZ. End of the issue. I find the answer. And even I don't need to worry much. Okay. But that is not the scenario. Okay. The scenario is that we don't have a constant T throughout the depth. There is variation. So we segregate in those parts where is one E is there and then the other E is there. Okay. So I segregated it. Now what I do? Now I take it out, take the E by rho term out, and I say E1 by rho y square dA plus E2 by rho integral to y square dA. Correct? So this becomes E1 by rho IZZ, okay, 1 plus E2 by rho IZZ 2. Correct? Y square d is IZZ. Now what is 1? So let's say 1 is a plastic core. So what is IZZ 1? IZZ 1 is moment of inertia of plastic core about Z, which is the neutral axis. If 2 is aluminium, so what is IZZ2? Moment of inertia of aluminium about Z. Okay, so let's find that first. This is mz. Let's find that first. What is IZZ1? Okay, so in the question, core is given to us. Core's dimension is what? Width is 200, depth is 150. Okay, let's find that thing. 1 by 12, width is 200, depth is 150 cube. Can anyone tell me what is this quantity comes? (56.25 into 10 to the power 6 mm to power 4). Correct. Now I will find IZZ2, that is only aluminum. So let us go back to figure. So I need to find about this axis of this area and this area. So one way is to do what? First I find about this area, about the centroid of this small area, and then I apply the parallel axis theorem to shift it here, and then make twice of it, because there is a similar area of the same dimensions at the same distance. One is this. Another one is I find this outer one with the aluminum and I subtract the inner one with the plastic. I will find just the value which I want. Okay. So what I will do? I will do the other one. Okay, without the parallel axis theorem. You can do with the parallel axis theorem also. It's little bit you have to multiply and then find the distance and those things. So instead of that, I will just directly do that. So width remains same, width doesn't change, only the depth change. So depth is total is 160. So I will make use of it. So it is 1 by 12 into width is same into 160 cube minus 150 cube. This will be the IZZ for aluminum. Now can you please obtain this? After that also some significant quantity is there. Okay, 10 to power 6. Okay, so this will be our IZZ2. Now in this formulae, you know E1 is given, you know E2, that is also given. You know IZZ, we just calculated IZZ1, you know IZZ2, we just calculated IZZ2, and we also know what is the moment, bending moment is coming. That is, what is unknown is the rho, okay, the radius of curvature, that is the unknown. That means we can easily find. So what I will do, I will rearrange that equation. So basically rho becomes E1 IZZ1 plus E2 IZZ2 divided by mz. Is it correct? Am I correct if I write like this? I just take rho 1 by rho common, I will multiply that rho there and bring the m there. Okay. Okay, fine. That means we can substitute our quantities and work with that. First of all, but just remember what is E1. So E1 is, I think, 800 MPa. Okay, and aluminum is E2, so it is, I think, 72 is or 1 72 GPa. Okay, 72 GPa. So I will write 72 into 10 power 3 MPa. Everything should be consistent. Now you have to find. So basically, what we do, rho is radius of curvature. So most of the time we are interested in 1 by rho, because as I told, curvature is the inverse of it. Curvature is 1 by rho. So curvature is more interesting quantity basically. So what I will write, I will also write 1 upon rho instead of this. So it will be just nothing but inverse of it upon E1, and you in most of the textbooks also you will find this way. It will be written 1 by rho, because that is more interesting quantity to work with. And mz is given 3 kilonewton meter, I think. Yeah, 3 kilonewton meter. Okay. So 1 by rho 3 into 10 to power 6, because everything should be in Newton and mm. So 1 10 power 3 is for converting kilonewton into Newton, and 1 is for meter to mm, divided by E1. E1 is 800 into ZZ1 56.25 plus this was 72 into 10 power 3 into 12.02. This whole is multiplied with 10 power 6. Now this 10 power 6 gets cancelled with this, so you have to calculate this quantity, 3 upon 800 into 56.25 plus 72 into 10 power 3 to 12.02. So if you can find this quantity 1 by rho, uh, 10.3.29 into 10 to the power minus 6, correct. It will come mm inverse, mm inverse, okay. So okay, now okay, this we found. Now what we need to find? Our question what was our objective? Let's see that first. So it asked us the overall thickness, this determine the maximum tensile and compressive stresses in the faces and the core. Means you need to find what is the stress at this top surface of the aluminum face and what is the maximum stress in the core of plastic, okay. And you know that in this case tension and compression just will be the signs, means signs will be opposite, nothing else will be different, quantities value will be same, just the sign will be, one is compression and another will be in tension. That means, so for if we look for plastic core, because that is easier to find, first we will focus on that plastic core. So I will draw the cross section once for clarity. Okay, so till here our plastic core is there. Okay, so how this will be varying, I showed you there also, I will just redraw it. I am just drawing now the stresses, I won't draw the other things because that I have already done. I will just redraw the stresses again. So this is the level and this is the level. So this is my plastic core, it will vary like this, and here I told it there will be a jump and then there will be a variation like this, and similarly there will be a jump and there will be a variation, okay. So you can see this is our plastic core, okay, and that other thing above is the aluminum. So you can see what is the maximum value of stress in plastic core, this is the maximum, this is the maximum stress, and where it is coming, at the interface of the plastic and aluminum. So I know at what point, at what y I need to find the maximum, okay. From this diagram or from this understanding I know where it will occur and I know how to find that. So I found that y max. So I found y max for what? Plastic, okay, and it is nothing but 75 mm. In this case it will be 75 mm, okay. So I know also rho. Now what is sigma? Sigma plastic, sigma is nothing but y by rho into E plastic or E1, if I say E1, okay, E1 is the plastic one, okay, that is all. So I know where the y will be y max divided by rho into E1. So y max is 75 mm, E1 is I think 800 MPa, and 1 by rho we already found, that is 3.29 into 10 to the minus 6. So, what will be this quantity? Can somebody tell? Yeah, 1 by rho, that's what, yeah, it has to be multiplied, not divided, yeah. 1 by rho is 3.29 into 10 minus 6. Okay, 0.1974 MPa. Okay, so this is the stress coming in, maximum stress which will come in plastic. Okay, now objective goes to aluminum. Okay, so for aluminum, okay, so for aluminum, what we will do, look at the diagram again. So, at this level we have a value of aluminum, and at this level we see it has increased like this. Okay, that means we need to find for aluminum at this level. Okay, for aluminum we need to find at this level. Okay, that means what will be that Y max? Yeah, 80. Good. So, the Y max will be for aluminum 80 mm. Okay. So, what we can do that, we will say sigma aluminum is nothing but Y max divided by rho into E2. E2 is our aluminum. So, it will be 80 into E2. E2 is 72 GPa into 10 to the power 3 MPa, and then into 3.29 only, yeah, into 10 to the power minus 6. So, can you tell me what this value comes? 18.95 MPa. Okay. So, this is the stress coming in, yeah, aluminum thing. So, you can see how much amount of extra, if you divide 18.95 with 0.1974, what comes? Just tell me the ratio. Sigma aluminum upon sigma plastic, max, what is the ratio? Ah, 96. So, is to 1, means the stress, maximum stress developed in aluminum is 96 times more than the maximum stress develops in plastic. Okay. And why it is? Because of the higher value of yield, of the high value of Young's modulus. This is actually because of the higher value of the Young's modulus, because it is having more ability to absorb or the load, or which will be like represented as a stress which is generates. Okay. So, this how we find. Now, I wanted to just let you introduce one more concept which is there, how to do the same problem, the second problem. There is something called transformed section. Transformed section. Okay. So, what we do in transformed section is that, as you have seen, for our case this beam was made up of two different kind of material. Okay. So, one was our plastic, another was aluminum. Okay. This is some different material and the rest is some different material. This is material 2, this is material 1. Okay. So, what, because it is a two different material means that it is not no more homogeneous, because you can see the E value, Young's modulus value is different for the other material. Okay. So, it is difficult that we can do, or we can manipulate the things as we has done with the homogeneous beam, in which only one material was there. So, one way we solved is using the conditions of equilibrium. We applied first the condition for the force equilibrium to find the neutral plane, and then we applied the moment condition to find, in this case, the curvature, and from that we found the stresses. Okay. Now, what happens if we have what happens if we want to work only in one material? Okay, we do not want to go, remember E1, E2, we do not want that, we want to just stick to one material. So, when we have that, we want to do that, then comes the concept of transform section. Basically, in transform section, what it says is that we want to transform this area, this cross section we want to transform. Okay. We want to transform this cross section into some another cross section, okay, whose dimensions will be in such a way. There are two conditions. This is the transformed section. Okay, this is called transformed section. So, we want to transform from this, which is the original section, to transform section. Now, in transform section, everything is material 1, there is no material 2, everything is material 1. Okay. So, we want to do this transformation from here to there, okay. But there are two conditions. Okay. There are conditions on which this can be transformed. What are the conditions? First, the position of the neutral plane should not change after transformation. Means, if we transform the section from this one to this one, the position of the neutral plane should not change, it should remain same. That is the first condition. Second condition is the moment capacity, or the moment, the capacity to resist the movement of the section, or the moment which we calculate of the section, should not change. Okay, these two things should not change when we transform the section from this inhomogeneous, because there are two different materials, to this homogeneous, because in transform section everything is homogeneous, but you can see that there are some extrusions, some extra parts which are protruding outside. So, how they come? They come due to some reason. What is that reason? The reason is that you define some quantity called modular ratio, generally represented by m. It is nothing but E2 by E1, where E2 is greater than E1, therefore, m is greater than 1. So, m remains greater than 1 and E2 is greater than E1, and this we called as modular ratio, which is defined as the ratio between E2 and E1. So, what we do, first we define this modular ratio. Now, what we do, wherever this material of different a different material is there, this E2 material, what we do, we find equivalent, because see, this material is there and it has been kept at a particular level from the neutral plane. So, I will give you a way to make it understand. Suppose this is the original section, which is here and here, and this is suppose the neutral plane. Okay. And yeah, this is the neutral plane. What I will do, before that I will draw a similar section, copy, paste. Okay, I am putting at the same levels. Now I draw the neutral plane. Suppose this is our neutral plane. Okay. So now what happens? This is the material 2, which is of high strength, this one, and material 1 is normally, this is 1 and this is 2. Now what is proposed here, that because there are two different materials and we do not want to work in two different materials, we want to work in one material. What we do, we first we define this quantity called modular ratio, which is nothing but E2 by E1. Okay. Then we do what, as I told, the what will should remain, the neutral plane should remain same, it should not change, and the moment capacity of the section also should not change in from the original section to the transformed section. Okay. So what we do, we need to find how much, means how much of the area corresponding to this, the stress taken by this area of the material 2 will contribute to how much area of the material 1 which will exert the same stresses or which will have the same force basically. Okay. So once again I will say, the force by this area of material 2, which will have similar way to the force which will be with the same area of the material 1. Okay. Now you see this material 2 is placed from the neutral plane, this NA neutral axis or neutral plane, in a sense that it is parallel to this neutral plane. You can see it is parallel, it is not like doing this or doing this, it is parallel just. Okay. There is a constant distance between here. That means this area only contributes or mostly contributes towards the bending. So similarly, if we want to transform it, we won't change this this centroid of this parallel, this area from this distance. Basically, we won't change this distance. Why? Because if we will change this distance, the neutral plane will change, and we have put a condition that the neutral plane should not change. So I won't change this distance. The distance of the centroid of the shaded area with the neutral plane, I won't touch it. I won't change it. That means I can't shift this area above or below. I can't, means I cannot change the width, this thickness. I can't change this thickness. If I want to transform in a new area which will be made of material 1, I can't change this thickness. That is not in my hand, because I can't change the neutral plane. That should remain same. The neutral axis should remain same. Otherwise, the problem will be a different problem. If I will change the neutral plane or the depth of the neutral plane, this distance, if I change, the problem will be a different problem. I am not solving a same problem. I will change the problem itself, but I can't do that. I have to keep the problem same. So I can't change this distance. Only freedom I have in this direction. I don't have any freedom in this direction. So what I will do, I will show you in the transformed area. First I will remove this one here, and similarly I will remove this one there. Okay. And I will do what, I will extend it by some length. It should be extended same, means if suppose like this, I will extend here and I will delete this also. There is no point, because it is the same area, same material, everything is same now. So sorry. Like this. Okay. Now it is all, everything is of material 1, nowhere material 2 is there. What is this distance? That is now most important part. We should know that, no. So suppose this was B, okay, and depth was D, total depth I will say D. So this distance now becomes M times B. Okay. it becomes m times b. How it came? I told you, you have to just equate the force. Force, total force in this area due to this material, if I should be equal to the force exerted by this material 1, means I have material 2 on the left side, I have material 1 on the right side. The force exerted or force you can say resisted, force resisted by material 2 on the left side or the shaded side will be same as the force resisted by the material 1 on the right side, that is all. Okay. This material here with width b resists a force F, that same force is resisted by this material 1 at here on the right side. So, that is how we come up with this, it is not some magic I am writing, that is how it comes, and what is m is defined here. So, now you have this area and now there is no issue at all, like there will not be, like you have material everywhere a single material. So, and because in this case you have the both thing above and down, the aluminum being above and down. So, obviously your neutral plane will be at the same this thing, and because I have maintained that the force should be same. See, I will write it again, so that you should remember it. Force resisted by material 1, I will say 2, that is shaded in the original section must be same as the force resisted by material 1 in the transform section. Okay. So, now you can ask me that you satisfied the equation 1 by saying that the neutral plane will not change. So, you are not extending this material above, like I am not making it something like this, I am not extending in the y direction, you have extended in the xz direction, that is fine, we are convinced condition 1 is satisfied. But how come you say that condition 2 is satisfied? I can say because as you know, I kept this distance constant by condition 1, I kept this distance constant, and by this condition I am keeping the force constant. By this condition, just I wrote here this statement, I am keeping the force constant. So, what is movement? Movement is nothing but the distance this multiplied with this force. So, I am keeping basically the movement constant, force into the distance into force becomes the movement. So, I am keeping that movement constant. How? Because I am keeping the distance constant as well as I am keeping the force constant. Finally, I am keeping the movement constant. So, I am satisfying both the conditions, that the neutral plane will remain same in the original and transform section first. Second, the moment will remain same in the this thing, in the movement capacity or the resisting capacity of the moment of the beam cross section will remain same in first in the original and the transform section. So, here in this problem we can find m very easily, we know E1 and E2, we can find m, and once we found m we can transform it in this fashion as I shown. Okay. And after that you know to find the maximum. So, at this plane till this point you know what is there, till this plastic is there, and this is your transform. So, you can apply the same conditions to find the value for the stresses. Okay. Yeah. 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 So, see, you want to find the moment of inertia, no, last time what I did, so basically you have this big area, but there is hollow regions. This is a hollow region. So what do? You find this big area moment of inertia with respect to this, which is mb into d cube by 12, correct. Now what you do? You subtract this one area, this you know, this is t, this remains same. I said we can't go or change this depth y direction. So this remains t, this remains t, total depth is I think 160. So 150 will be this one. So what you do, and you know this much portion, this is total mb, this is b. So this will be what? mb minus mb minus b by 2. See, this will be mb minus b by 2, that is m minus 1 into b by 2. So you know the width, you know the depth, cube by 12, twice of that you minus from that you will find the total IZZ of the section. Or you can, if you find that very like this thing, you can use the parallel axis theorem. You first find about this, then transform it to this axis, and for this for this portion you can easily find that also you can do. So basically in this equation only where I wrote, yeah, here. So you here only you have one term, E1 by rho into IZZ, that is all. M will be incorporated in that. Basically, yeah. So basically, what you will do for E2, you will write in terms of E1. E2 will be become M times E1. You understood, no? E2 will become M times E1 because I have this M defined as E2 is equals to M times E1. Correct? Yeah. Yeah. Yeah, actually, yeah. So what happens because of the transformation? You can either, so I am giving you a very easy answer irrespective of today's class, because you have already defined the equation. Okay. Now you have transformed your area. This is not in a transformed thing, because see, either you define one IZZ which will be of the transformed IZZ, then it is correct. If you define only one IZZ which is of transformed, then you do not need this. This is not required. But if you, because if I talk in two parts, now I think you understood. If we talk about two parts, one part being this part and another part being this part, then you can use the above formula itself, this formula which I am saying. This formula we can use. If you are saying no sir, I want to just to use one and I will find IZZ of one thing, then no issue, you just ignore it. Just find IZZ of the whole transform section, have E as this, defined rho as this, that is all. You know the moment, you can find this by putting this IZZ there. Okay. Yeah, and wherever you will need to find in the value in aluminum, you need to invoke this, you have to use that, because in aluminum you will say E2 into some epsilon or E2 into y by rho. Now E2 will be M times E1. Correct? Yeah. Yeah. Yeah, yeah, sure. Yes, that KD. First you have to find the KD. Yes. So yes. So because you, you can just find out the KD. Even because no, you can use in that also. Okay, I'll show you. You can use in that also. See where I used. This one, no. See, so here you can use transformation directly. You can say E2 is nothing but N times M times E1, and directly you can make it in a one E1. You can use that also. Yeah, you can use. Even in this case also, see, I never used about any concept about neutral axis, because I told that is a condition. The neutral axis should not change. It is a condition. So I never used about anything about neutral axis. I just drew this section. Now I know what is the depth, what is this width, depth remains always same. only width change in width occurs, correct. So, you can directly invoke the force equilibrium here itself without the E2, but just remember you have to do wherever you have to find some stresses in, because see what this diagram tells us, this diagram tells us the variation of strain will always be continuous, it will never be discontinuous at the interfaces where the two different materials are meeting, only there will be a discontinuity or the jump in the stress. So, you have to account for that jump. So, wherever you find the stress in material E2, you have to replace that E2 by m times E1. Okay? Yeah. Yeah, we can start from the beginning stability transform. So, first of all we should know the ratio. If we have the ratio m, that is a modular ratio, we know that what will be the depth, what will be the width of the transform section of that much area. Okay. We will know that width of the transform section. Once we know that width of the transform section, we can draw the transform section, because as I told you, this part will only be translated at the same level of y. This y can't be changed, only change allowed in this, correct. Yeah. 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 Okay. Okay. No. What I am trying to say, no. I understood your point. Suppose the material is only here. Okay. Now, what happens? What I am trying to say, the change in neutral axis. See, because the there is only second material is in the below. There is no material 2. There is no symmetry there. Obviously, due to this, the neutral axis will shift from the centroidal plane in this. Okay. If you don't have any concept of transform section, just forget for 1 minute, there is no transform section, you don't know what is transform section. By intuitive also you can tell from its centroidal position, obviously the neutral axis will shift, in this case it will shift towards below, because you have added below a different material. Okay. Mostly below, because if I consider the other material is more stronger, so it will shift below. Okay. That shift is allowed. But I am saying, if I am drawing this, if I am finding a neutral axis depth for this and I am finding a neutral axis for depth for the transform section, then the two case it should remain same, it should not change from here to there. Okay. In comparison to this, if I draw this, in comparison to this, the neutral axis will change between 1, 2 and 3. Between 1 and 2, neutral axis depth will change between 1 and 2. Obviously, in 1 the neutral axis depth will be at the centroid, it will be the centroidal axis, but in the 2 neutral axis depth will not be the centroidal axis, it will change. But what is not allowed, between 2 and 3? 2 and 3 should not change. For 2 as well as 3, neutral axis depth should remain same. I hope now I made it clear. Yeah, because what I am doing, because I am nothing, I am not changing, I am just removing some material which of different kind and putting material which of this same kind, that is all, with a width, extra width, that is all. Yeah, so I am, it would have changed if instead of this my transform section would have been if suppose I little bit increase like this. If I change this, no, this will cause a change in the neutral axis, because I have made a higher depth than the required. Okay, this will, yeah, yeah, yeah. Hmm. Yes. No, that's what I'm saying. Even if you don't find at this stage in 2, you can find KD here also, because here you will be dealing with 2 different material, even you can deal with 1 material. If you go to the lecture, I think sir has found in this one, I think professor has found in this stage. So even you can find here also, that's not a issue, okay, just you have to convert it appropriately. Okay. Otherwise, if you are able to understand that, that is very fine enough, no issue. You find KD here itself, no problem. You, in that case, it is a concrete example. So you have some reinforcement bar here. So you say there is no tension in concrete, means concrete does not take tension, only it takes compression. So you say find this force, you find the force due to bars and you equate it to find KD. Yeah. Yes. Yes. Yeah. 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 No, but if they want to find the capacity, they have to find the moment. No, if they want to find the capacity, they will just find the moment. Yeah, so they have to find the moment if they want to find the capacity m using that. So they have found, I think, capacity they have found using that, means, or whether the 3 bars are sufficient or not. They have found that. Yeah, whether 3 bars will be sufficient or you need more than that, because in this I think movement is given, how much movement it has to be subjected to, that is given in that. Yeah. 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 You are saying how to find KD. Yeah. So see, if suppose in this case you know you don't have KD, but you know this width, correct? You suppose this is B, this is m times B. Okay. So you need to find neutral axis depth. What you will do? You will say the force in this region as capital C, total force, usually compression, and you will say the total tension in this region. You can find that using the variation, same variation. Just your width, after this point your width won't be B, it will be MB. Yeah, exactly. After this point that area change will be playing role. Yes, that integral. Yes. Yes, so you have to divide it into 2 parts like this. You will have this one and this one. So you have to find the forces in the 2 differently. Now stresses will be correct, same, but the area will increase, no? Yeah, area will increase. Correct? Yeah. Okay. I hope you guys able to understand. Yeah. Yeah. You go once, yeah. I would request all of you to go once through that same problem, concrete problem. You will be having more clarity, because and if some of you are from civil engineering background, that is the most one of the most important fundamental thing in the design course of in civil engineering, concrete design, because this is a concept mostly used in civil engineering concrete design. Okay. Yeah. Okay. So I hope you guys all understood. Okay. Thank you for your patience, and thank you for today's lecture. No, that's fine. Yeah. That's my part of my job. That's fine. Okay. Okay, then we'll stop for today here. Yeah. Thank you. Thank you all for joining. Thank you so much. Thank you. Yeah. Bye. Thank you. Thank you, sir. Thank you.